pleasure for me to be here today and give a plenary talk as part of this opening ceremony, reflecting a bit on the evolution of computational electromagnetics. In doing so, I realized how many decades I have been involved in this journey, and look a bit also at the state of the art and where the journey is taking us. As part of the agenda, I will review a bit the different techniques, really high level. I mean, there's no time to go low into the very detailed, full wave electromagnetics, high frequency asymptotic methods, hybridization, look at some specialized solutions, even with these standard techniques, even with the modern high-performance computing hardware. It's still challenging to solve specific problems, so specific solutions have evolved. I'll reflect on a few of those, spend some aspect on looking also at multi-physics problems. Often electromagnetics is not in isolation, it's coupled, for instance, with thermal effects. Look a bit into advances also that came along with the methods itself on the high-performance computing side. A very hot topic in recent years is AI, ML, machine learning, artificial intelligence. Will this replace all our traditional approaches, or how it can complement, help? I have some thoughts, some examples there, and at the end, some conclusions and future outlook. And as part of the overview of the EM solver technology, let me start going back, and I really don't want this to be personal history, of course, or in any way, you know, you mentioned FECO. I mean, I'm using examples of FECO, but there are, of course, many very good, very powerful other tools, academic tools, commercial. Many companies have in-house tools. So I'm just using this a bit as examples to take you through the journey. And my very first exposure to computational electromagnetics was as a student. I was assigned a project to do some modeling. There was an existing code, NEC, Numerical Electromagnetics Code, from the Lawrence Livermore National Laboratory in 1991, and I was kind of writing a preprocessor, a mesh generator, and have a graphical user interface, and the MS-DOS, the Turbo Pascal, and implemented an iterative solver, Krylov subspace method complementing the direct solution. And what you see here is an aircraft model back then. 29 wire segments, and this was useful, you know. And as time passes, I will show you later, 34 years later, these are the type of aircraft models we solve with all the details. Sometimes, you know, everybody inside wants to have wireless communication, so one does propagation modeling inside, where to put the wireless repeaters. And I just saw last week one of our results. You know, of course, the most important people in the business class sit in front, and you must make sure that also in the very front seat you have best radio coverage, good data bandwidth. And interestingly, this model has 30 million unknowns. With the advances, and I will have later some slides showing you the advances in computing power, it almost takes the same time to solve this problem. From 29 unknowns to 30 million, much more accurate. So this is a bit the underlying theme of this presentation, to take you through evolutions in the methods in the computation. And just to round off a bit my personal story, in the same year, 1991, I started my master thesis, and I was tasked as a part, I think we were actually the same research group from the German ministry, funded R&D project on EMC, shielding, truck cabins. So I kind of, with a rather implicit basis function, started to write a software which became FECO based on method moments. Of course, there are many more problems apart from EMC in radio science, computational electromagnetics, antenna design. Very important to take the environment into account, where the antenna operates, antenna placement, looking at unwanted effects, not only from EMC, EMI, cable harness coupling, but also bioelectromagnetics. And I see there's another plenary talk. up to, I've already mentioned, propagation modeling for in-cabin scenarios like in an aircraft, but also, of course, mobile communications within urban and rural environments. All these problems can be classified a bit by the complexity, simple wire antennas up to very complex structures with many materials, but also a very important criterion for computational electromagnetics is the so-called electrical size. So that's the size in terms of the wavelength. Is it electrically small, electrically large? And dependent on which problem one deals with, there are different methods, many more, that can be classified as full wave methods, finite element method, finite difference time domain, method of moments, accelerated versions, AIM or MLFMM, but then there are also high frequency methods based on optics, physical optics, ray launching geometrical optics, or some call it shooting and bouncing rays, a uniform theory of diffraction. And what is very attractive is actually to combine these two, because sometimes you will have a simple wire antenna mounted on a ship, and there is not the one method being able to deal with both, and this is kind of the combination, combining different methods to solve the same problem, taking all the mutual coupling into account. The first, and I'm really kind of touching on the high level in this presentation on the different methods. First combination, and it's very popular, done by many research groups and for many, many years or decades, is kind of combining finite element method with integral equation methods, or also the accelerated version, MLFMM. The motivation for doing so is sometimes one has complex problems like human phantoms, different materials, volumetric problems, exposed to electromagnetic structures which can be closed like a cell phone. Then actually everything can be solved with finite element, a finite time domain, but it can also be far away. Like here, this is human exposures to a base station antenna, which might be 10 meters on top of a building across the road or something like this. And there again, for these type of metallic structures, integral equations are very suitable, but finite element with discretizing the whole space, the whole road, the airspace in between will blow up the computational problem. So coupling kind of these methods, leveraging the best of both technologies, is a very attractive way of doing so. You see here one example. This is a human body exposed to an MRI system. There is a bone implant, and one can kind of, with this hybrid method, model the electromagnetic fields in these MRI systems with integral equations coupled into the human phantoms through finite element. And I will only later touch on multiphysics, but this is already kind of the first example. Knowing the field distribution around that bone implant, one can couple with thermal solutions to also get the temperature distribution, which is really the critical quantity to ensure is it safe to put these patients with such implants into such MRI systems or not. Another hybrid method, and this is also where I personally through my PhD got involved, is combining full wave methods with high frequency asymptotic methods to solve problems that are electrically large. And also I think this evolution over the last decades, what is electrically large, what is the boundary where a full wave method is still acceptable to use, has shifted tremendously. There's almost this kind of constant, an engineer is willing to wait a night for a result. And earlier it was a small problem that you could solve overnight, or maybe sometimes you can afford to wait a weekend. You submit a job on Friday, but Monday you want the results. These days, of course, much, much larger problems can be solved full wave, but I think what is interesting in communications, frequencies get always higher and higher. We are now already doing hundreds of gigahertz, terahertz communications. The problems people are interested in solving are getting larger and larger. Earlier you were fine to model an antenna in a small region around it. Now you want to model the whole aircraft, the whole ship in ranges of gigahertz. So this is why these methods always remain relevant and important, just the boundary where they are used shifts. Combining method of moments with physical optics is very attractive because both of them are based on modeling or representing currents as an intermediate quantity before then in the second step evaluating the scattered or radiated electromagnetic fields. One can subdivide a scattering area into a full wave region, an asymptotic region, have bidirectional coupling, so the electric method of moments currents radiate, cause a magnetic field. That magnetic field is incident onto the physical optics region, is causing physical optics currents with the usual approximation. These currents in turn radiate electric or magnetic fields back onto the moments region and again influence the solution area. This can be solved as a closed form system, changing the method of moments matrix equations. It is also possible to do that, we quickly jump to this slide, in an iterative way, very much as I just described it. Both methods is good. And here just one example. This is a Cassegrain horn antenna with a subreflector, main reflector, the horn antenna and the small first subreflector are assigned to the method of moments, or in this case MLFEM, the kind of accelerated version of integral equations region. The main reflector is dealt with physical optics. Also by doing it this way, one avoids to have double reflections, the PO region, which can be sometimes time consuming. And you see here kind of three results. Blue reference solution, everything full wave. Red hybrid method, MLF and MPO. And there's another solution, the dashed line, which we call as a large element physical optics. And this is not using electrically small mesh elements, but a few lambda in size with phase variation. And you see overall, all three methods agree very well. This is a zoomed view around the main beam. You hardly realize that there are three curves. Only if one looks far away on the side lobes, which are about 70 dB below main level, there is a difference of the dashed line. But this is actually not because the solution is inaccurate. This is because we use a large mesh, a few lambda, and we represent that curved surface. So we are actually solving a different problem than the other two solutions. Shooting and bouncing rays, or as we call it, ray launching geometric optics, also a technique used very often and very popular for electrically large systems, and it can also be hybridized with the method of moments in a similar way than I just described. And it basically is launching rays from a source, could be a point source, antenna, could be an incident field, incident plane wave field. These ray beams interact with the geometry. If these are metallic structures, there will be purely reflection, similar to the PO currents. Could be, of course, metallic dielectric structures with partial penetration, transmission, partial reflection, and so forth. And there can be multiple bounces. One can complement these techniques through creeping waves, edge diffraction, adaptive ray splitting, and all these fancy things. Just an example, again, comparing full wave. This is a project modeling radomes around the front section of a helicopter with frequency selective surface elements to protect weather radar antennas and so forth. You see here a full wave solution with a multi-layer radome, including the FSS structures. And on the right, you see methods for shooting and bouncing rays, where one can also accelerate the solution by creating lookup tables, kind of evaluating the reflection and transmission coefficients of such radomes as a function of frequency, angle of incidence, polarization, and use those as part of the ray structured interaction formulations. And you see also here very nice agreement. And I just want to point out another kind of improvement that has emerged in the last few years, similar to what I referred to earlier with the large element physical optics. Also here, of course, the higher the frequency, normally the more rays need to be launched to still satisfy Nyquist criteria, kind of have at least 2 rays hit the structure per wavelength or so, which again provides a limit if the structure gets really, really electrically large. Like here, this is now a whole ship at 10 gigahertz, and we look here at the near field exposure radiation hazard in this area. This is kind of the near field plot. By combining different methods, launching electrically large ray beams, which can really be 10 to 30 lambda in extent, and then these big ray beams hit the structure. Of course, sometimes they will hit maybe a uniform, flat, smooth surface. Nothing needs to be done other than making sure one properly evaluates the radiated fields accurately over this large cross-section. It's of course not sufficient to represent it by a single point integration, but there might be situations where the ray beam, a part hits an edge, part misses it, and so forth, so we need some adaptive splitting and all these fancy things. And by such operations, I've just picked this example, instead of, for instance, 442 million rays, one can reduce it to 367,000, and in terms of runtime, it means a factor of 230 faster, without anything that you realize if the results will change. And this is now the last method I would like to introduce quickly, which is the uniform theory of diffraction, also around for decades. It's kind of not ray launching, kind of shooting rays in some grid onto the structure and let it interact with the structure. It's kind of really having a source point, having an observation point, finding the rays, so that is ray tracing, that are either the direct line of sight or reflection, multiple reflections, diffractions, creeping rays, and so forth. And traditionally, often one has canonical objects, and geometries need to be relatively canonical to apply UTD principles. There have also been evolutions to apply UTD to general, arbitrarily curved structures, like here, where it's not so easy to identify what are the flat parts and where are edges and so forth. But it makes it just much more realistic, and this is the expectation. Nobody will buy into the next generation of antenna design if you use a car model like this. And this is where I come back to this more modern aircraft, now not with MLFRM, 30 million unknown here, purely UTD, and also here, I'm not going into all the details, there have been a lot of methods and extensions, especially also on the geometrical processing side, to make sure all the ray tracing, which in this case is often the bottleneck, it's not the computation of the fields, it's finding the rays in the first place, how that can be accelerated. And I just want to show one example, and this is now really a method which is truly frequency independent. If you solve a structure, this is now antenna placement on a helicopter, if you solve it at 1 gigahertz or 2 gigahertz, nothing changes except for the fields that are computed. But the rays, if the mesh, if the geometry is the same, the ray path are the same. So this method is really truly scalable if frequencies go up. And it's very attractive in terms of runtime. What makes it maybe a bit more challenging here is to combine with full wave methods. It's not so easy with physical optics where everything is based on currents. Here one has kind of certain structures which are based, if it's UTD, with fields, ray tracing, and others with currents. So one needs to have special half basis functions to model connections. Also sources for UTD, normally one needs to have a certain separation. It needs to be in the far field, but if you have antennas mounted on a structure, you're not on the far field, you're actually connected. But all this can be solved, and one can get very accurate solutions. This just shows really academic, simple problem, but it is kind of UTD plate, method of moments, dipole antenna, the distance changes. This shows the input impedance of the antenna, full wave compared to hybrid method, taking all the coupling into account, and you see very, very close almost touching, it still works perfectly. Kind of concluding this general overview of different computational electromagnetics methods, full wave, high frequency, I want to move on to some problems which remain challenging with these methods, but where there are special solutions. And unfortunately, I had to be very restrictive in what I select, given the time constraints. And I try also to be kind of relevant what practical antenna design engineers are facing, the challenges they face day to day. And one of those, for the last kind of 20 years, has been nobody wants to drive around in a car where there are all these antennas sticking around and they can be broken, and you forgot, if you have your car washed, you forgot to move it and it's broken. All these more and more communication systems evolve and all these antennas are integrated somehow. And one of these technologies is to leverage the wires. Often they are, in any case, due to the heating system in the rear window of a car, already some wires embedded, and one can leverage these as integrated windscreen antennas. It might look simple, in reality it is not, because this is not just a glass where there is one wire printed on top of it. It's kind of a multi-layer structure, can have up to 7 different layers, different complex materials, and it is a challenge. I mean, of course, you could say, oh, no problem, we just use final element method, final difference time domain, we discretize, but if you look, some of these layers are extremely thin, nanometers, and also final difference time domain makes it challenging because the windscreen is not flat. I mean, it's curved, it's nicely fitting the car structure. So all these elements make this problem actually very challenging. And you can't just ignore the effect of glass because it is a dielectric which influences the resonances of your antenna and the radiation characteristics, of course. So there are also ways of kind of leveraging multi-layer planar Green's function, Sommerfeld integrals, for evaluating correction terms for the matrix elements. And of course, it's not, nobody's driving around with an infinitely planar, flat windscreen. It is an approximation. The curvature needs to be accounted for, and the fact that it is finite. But one can get actually very good solutions, and then it boils down to solving actually the problem like in free space with additional correction terms. And all the overhead of discretizing this multi-layer windscreen is avoided. And you see here one result, which was an Audi antenna design compared to measurement, the windscreen antenna solution, numerical solution in red, measurements in blue for magnitude and phase of S11 of this antenna design system. Another challenging but yet very, very relevant problem is modeling electromagnetic interference susceptibility for cable harnesses, combined with other structures like windscreen antenna. So this is, for instance, a windscreen antenna and a car structure, and in a car, of course, they're not just these 2 cables, you have kilometers of cable harnesses with complex bundles and multi-layer hierarchical structures. So there can be individual wires which have a shield, they are part of another higher level bundle with another shield. And also modeling this is extremely complex. You can't just say, oh, we just discretize everything. Kilometers of cables with, as I said, multiple wires, multiple hierarchical shields, it's impossible. It's possible for simple, if you have one wire in the laboratory running on a table, like a CISPR 25 setup or something like that, but in reality it's not. But also here, luckily, there are solutions. One can combine these full wave or asymptotic electromagnetic techniques that I've touched on so far in the earlier part of the presentation with MTL, the multi-conductor transmission line theory, which converts all these internal details of complex cable bundles into an equivalent SPICE network of circuit elements, or a network of circuit elements which can be solved with a SPICE solver. So essentially, the electromagnetic field problem is reduced to looking or solving the interaction of the structure with the outer shield which is kind of represented as a single wire, one could say, and with the transfer impedance, one can go into the internal of the cable, the outer cable shield, and solve everything inside with a circuit solver. Also here, it's actually important, if you do that, you end up with SPICE net lists, which can have hundreds of thousands of circuit nodes. And we have compared, as for instance, Berkeley, the original Berkeley SPICE solver, or NG SPICE, the next generation SPICE, an open source project. One can use those SPICE solvers, which are general purpose circuit solvers, but one also can tune and optimize a circuit solver tailored for these type of net lists that emerge from cable harnesses. And you see here for 3 examples that one can actually get up to 2,000 times faster solutions of the SPICE-related part of the circuit problem. Of course, there's still the outer problem of the car or aircraft, whatever, with the electromagnetic field solver, which is not affected by this one. Also here some examples to validate, and this is again actually a very simple problem. It's just an L-shaped cable, which is simple enough that one can use a full wave EM solver as reference. So this is the blue line, everything with method of moments. Then we have 2 combined solutions, hybridizations, multi-conductor transmission line theory, the one with method of moments and the other one with fundamental standard. And you see here also, for purposes of EMC coupling, reasonable agreement. I mean, it's not perfect. There are some differences in some reasons, but people dealing with those are very, very happy to get these type of accuracies. More complex problems, of course, can be solved. This is now, and it's apologize, we can't really see the cables. There are actually some cables running here. These are cable ports, and one can look at the induced currents. So one can also apply these techniques then to more complex problems. Another more advanced feature is not only splitting up a problem and using different methods as in hybridization, but actually going one step further in kind of really doing model or domain decomposition. And a nice example is here a feed structure illuminating a horn, dual-ridged horn structure, where one can even combine measurements and computational electromagnetics. So in this case, the horn antenna was measured, the near field was collected on a box around, and this equivalent near field aperture was used in the electromagnetic, computational electromagnetic solution as excitation to look at the interaction with the reflector. But it's not only, of course, limited, this kind of splitting up the domains, limited to combining measurement and computational electromagnetics. One can also apply the same principle to splitting up a large complex electromagnetic problem as such. This shows, for instance, a slotted waveguide array. It's very similar to the earlier example I had for the helicopter with the shooting and bouncy rays. Here we have again a slotted waveguide array example as a radar or weather radar antenna. In the front section of an aircraft, there is a radome which has frequency selective surface elements, and solving the whole problem can be or could be too time-consuming, might require too much memory for your computer, so one can split it up. As a first step, solve the slotted waveguide antenna in free space, obtain either, as in the early example with measurements, near field on an aperture, or spherical mode representation, or even a far field pattern, and then in the next step, put the structure around, like here the radome, and a source, use this equivalent representation of the true antenna. Domain decomposition is similar principles, splitting up different problems with full coupling. Here it's the non-conformal version where one splits, for instance, these rotating blades of this drone. Here is the green line indicates the boundary, and what is nice, there is no remeshing. So the meshes at the top and the bottom stay fixed, and as it rotates, of course, the meshes will not be connected as they normally should for basis functions to be set up properly, for currents to flow across the boundary. But there are also many different techniques how to kind of represent the continuous current flow even in those situations, allowing then a very efficient solutions and modeling of kind of these moving objects as well. And I thought I'd put that part here in characteristic mode analysis, which is also a kind of an advanced solution. It's not new, it was developed in 1971, or it was earlier. There was some work by Gabas, and then Harrington and Mautz kind of published it in 1971. But nobody, I think it seemed nobody really cared, and nobody really knew what to do about it, and it kind of got forgotten. But the last 10 years, it really came back as a very, very powerful tool to understand how structures can radiate and how antenna design can be mastered in a very efficient way, leveraging not only the antenna but the whole structure. And essentially it's based on method moments, kind of splitting the method moments matrix into the real imaginary part, solving an eigenvalue problem, and one gets these kind of so-called characteristic modes, and associated with them, each mode also has a far-field, near-field distribution, and knowing how a specific structure can be excited and can already kind of radiate allows in a much more intuitive way to then excite those structures through antennas and leverage, as I said, not just the antenna, but the whole structure. And as part of these advanced methods, an evolution has certainly also happened over the last decades related to propagation modeling. With our ever more and more connected world with IoT sensors, mobile communications, wireless LAN, evolution from 5G to 6G and so forth, it's always more and more important to have sophisticated and important also fast. Sometimes these people want real time. You know, as certain things move around, as a car moves in a city, one wants to have real time evaluations of certain communication systems. So there have also been an evolution in different technologies based on what I introduced earlier, shooting and bouncing rays, ray tracing, many heuristic propagation models that can describe these different things. For 5G and 6G, it's even more complicated, combined with different beam steering, multi-beam pattern antennas, or so there are also some special sessions and papers here, this conference about these reconfigurable intelligent surfaces, where one can kind of have arrays, passive arrays mounted on some walls, and they will kind of selectively steer the beam in certain directions, where there's maybe a group of pedestrians and needs more bandwidth and more coverage in a specific street, which is not directly visible from the base station. And all these are, of course, supported and driven also by the advances in computational electromagnetics. Also here combining, for instance, I touched earlier on the windscreen antenna. This is now another modern design of hiding the antenna in the mirror, in the outer mirror, and one can also use kind of the methods I introduced earlier to compute radiation patterns of such an antenna, put then such a vehicle in an urban scenario, let it drive around with ray tracing combined, and one can kind of replace or complement these drive tests through virtual drive tests in the computer. This shows one result of a measurement campaign and the corresponding simulations. And of course, it's important also to notice if you repeat the measurement 5 times, you will get 5 different results. There might have been rain, suddenly the ground is wet, it's completely different. It might happen You know, at one position there might be a truck passing by, just to get the blockage for a few seconds. If you drive the same road again, an hour later, there might be no truck at this position, there might have been a truck a bit earlier. So it's really a few dB up and down, nobody cares. It's kind of looking at averages. And I think I like this story very much, showing that computational electromagnetics is not only relevant on Earth. This was a study by the NASA Jet Propulsion Laboratory ahead of the Mars mission, looking at the communication link between the Mars Perseverance rover and the Ingenuity helicopter. And what is very important, as this helicopter is flying around on Mars, that it does not lose the radio communication link to the base station, because otherwise the base station can't tell it anymore, please turn around now, it will just be lost. And that, of course, has a huge impact. So they did a lot of propagation modeling studies on Mars, and actually when, and I don't have all the results, but when the mission happened, it was recording the signal strength in real time while on Mars, and later on they were comparing to the simulations ahead of time, and it matched really well. Leaving that block of computational methods and some advances, and just touching a bit on some multiphysics structures. I had already the thermal impact of EM fields for that MRI example. Sometimes there are also pure structural mechanical implications, like here a radio astronomy antenna, which is of course a big massive structure which has a weight, and dependent on the angle there is the different effect of gravity. Gravity causes deformation, there might be wind impact, so one can actually combine computational electromagnetics with structural analysis for each position, look at deformation, use the modified geometry, repeat the electromagnetic analysis, and you can actually see changes in the radiation pattern just due to these deformations. Another multiphysics coupling which I want to show here is again related to radomes, which I had already two other examples in this talk. A radome is not standing still on Earth. Typically a radome in front of an aircraft, this aircraft will fly. In flight, there is aerodynamic pressure, which causes deformations, but also which causes heat. That heat will change the material properties, so it's also kind of a multi-dimensional coupled multiphysics problem where the electromagnetic properties of the radome change if you measure it in an anechoic chamber on ground versus if you operate it in flight at a high speed with all these impacts. And also coupling different electromagnetic and structural and thermodynamics codes, these problems can be addressed. All these multiphysics, electromagnetics codes or numerical algorithms rely, of course, on computing hardware, high-performance computing. And I've put here a bit the evolution from the 90s up to today of the top 500 supercomputers, and this gives kind of the lowest of these 500, the average, and the top computing power expressed in floating point operations per second. And of course, every grid here is a decay, factor 10 faster. So you see already here, we have gone through a huge evolution in the last decades. But I think it's important to realize there is a benefit which one gets for free kind of out of that. But, and many of you are of course active in this domain, I think it's always still very, very important to find, and this is, sorry, I went back, this is actually my first bullet item here, one needs to have still smart and powerful algorithms in the first place, like going from an n squared or n to the power of 3 algorithm to something like n log n. It will always beat any advances in the computing power. And you can still leverage, of course, the advances in computer power as an additional acceleration. So this is always where to start. But then once one has a great scaling algorithm, which is still accurate enough for the given problem, then one can and should, of course, leverage all those modern architectures like distributed and shared memory parallelization, GPU computing, use special libraries where others have an assembly level, provided low-level mathematical algorithms, and so forth. And then, yeah. And I think coming back again a bit into history, I was privileged enough in 1997 to get access at the Computational Center at the University of Stuttgart to a Cray 3 supercomputer. It was very expensive. Every CPU minute one was built and had to justify why one needs this. And I was able to solve this problem there. Let me explain a bit. There is an automatic learning system at the end of the runway at an airport, and it provides kind of the signal for incoming aircraft to land. And it's a highly sensitive signal. It's almost kind of like the incoming aircraft is on a null at the pattern of this system. But there are, of course, and you all know that you have been sitting there for half an hour waiting for takeoff. Along the runway, there's the taxiway, where there are aircraft queuing up to wait for their turn to start. And these aircraft next to the runway are kind of electromagnetic scattering objects. They will interact with the signal of this antenna and disturb it. And this is kind of what is indicated here in red. It's the error due to the presence of these aircraft. And it's very important, of course, not to have a disturbance which is high enough for the incoming aircraft to land along or next to the runway, but to still have a safe incoming flight. So I was kind of solving this problem on a Cray T3E supercomputer, method of moments, 36,000 basis functions. This machine had 512 CPUs. Back then, of course, one CPU had one core. I could use 384. It was running 1.7 hours, so kind of the CPU time was 27 days. With physical optics, still reasonable result. I could solve it on my back then Pentium 2 computer, 35 minutes. I was solving the same problem last week on my laptop computer. And you can see 2 minutes instead of a supercomputer. With MLFMM, it's even less than 5 seconds. Physical optics, fractions of a second. So this also just shows, in practical terms, not just these graphs and floating point operations, this shows really what it means in terms of impact for computational electromagnetics, what the advances in computing power have brought us over the last couple of decades. GPU acceleration, I have just one example as part of shooting and bouncing rays. Here it's kind of 40 times faster, leveraging GPU instead of CPU for a shooting and bouncing ray problem. And my last block before coming to the conclusion is devoted around AI, ML, where one sometimes hears, these fears or slogans, oh, this will replace all engineers in future, everything, all the decisions will be AI-driven. There are, I think, and I would hope I can show this to you, certain elements where it can really help to get to better solutions faster, but it's really only complementing traditional solutions like measurements or computational electromagnetics to create certain data points. And machine learning is actually nothing that fancy. It's more mathematics. You have a set of data, could be either existing historical data that was collected, or it could be data that is generated through measurements, computational electromagnetics. One trains machine learning models, one has other data, evaluates, is the model sufficiently accurate enough or not? If not, there's an evolution, retraining phase, and in the end, it's kind of applied within, and that's also important that one knows the bounds of confidence within these bounds. It can be applied also to new inputs to create results much faster then if you have to build a prototype and do measurements, or if you have to redo your computational electromagnetic simulation. There are many, many machine learning algorithms, of course, way beyond the scope of this presentation to discuss. They can be classified into certain groups, but I would just like to show you a few examples. The first one is more related actually to the data processing. Often one is challenged by the complexity of certain problems. So this is an EMI related vehicle in unity test. There's a vehicle exposed to electromagnetic fields. One has to decide on certain critical aspects. And we maybe go to this example. So there are different components in this vehicle. Of course, in reality, there are even more. Here in this test, 30 different components or different positions were considered. The frequency is, of course, a variable here, 20 to 400 megahertz, different polarization of the incident field, orientation of the antenna, but also, as you all know, if you order a car, there's not just one car. There are many different configurations and versions. Some have, for instance, a sun glass rooftop, others have metallic glass, metallic roof, and all these different combinations. You have a huge, huge number of variations, and it's almost impossible to cover all those through numerical simulation. But yet you want to know what is the critical combination. Is my specific device safe to be used? Here it helps with machine learning and decision trees. For instance, here, just an example, to identify what is the critical combination, which component at which frequency for which car model is something that might maybe exceed certain safety limits. Another example here where machine learning can really help to reduce simulation time. This is an integrated radar antenna that was designed. It has many different parameters, all these width and length and separations. And when you manufacture it, there will be tolerances. And the task was to ensure what is the sensitivity, are there certain combinations of tolerances which will make the antenna to be outside the design specifications. And one can now, of course, set up a parametric study and vary all these parameters, kind of a design of experiments, but you already see here, and this is just a heuristic assumptions here, if one simulation takes 3 minutes, 100 simulations will take 5 hours. If you need to do 10,000 combinations of different parameters, it will already run for 21 days. So it's kind of linear, of course, with the number of combinations. And the machine learning model, the runtime, it can be evaluated really very quickly, 20 microseconds. So there, 100,000 combinations of parameters to evaluate, it would take 200 seconds instead of 21 days. A last example, or not the last, there will be one more, but one related to radar cross-section and design of stealth aircraft, which was also used, and it's a bit difficult to see. These are all different aircraft. They have, maybe you can see some have a bit a longer wing and other have a bit other tail section. And this is available historical design data. It was kind of used to train machine learning models. These machine learning models, and it's very important, you shouldn't just blindly trust them. One needs to validate and verify with given sets that were not used to train it, is it still within the range of confidence what the results give? And if yes, one can apply and also in fractions of seconds get the corresponding results. And the last example, how AI and machine learning can be used, is related to setting up a 5G network communication system in downtown Munich. The goal was here to reduce from originally 11 base stations, 11 antennas, to only 5, still giving sufficiently large coverage, and the threshold was here receiving field strength level minus 80 dBm. And with machine learning, optimizing the positions or orientations of the antenna, that goal could be achieved. And power from 11 to 100,000 tons, which of course is again a huge impact on cost and operating costs for setting up such networks. With this last example of machine learning, I would like to conclude and just summarize a bit this presentation. I have started giving an overview of computational electromagnetics, full wave methods, hybrid methods, or high frequency asymptotic methods, the combinations through hybrid methods as they have evolved over the last kind of decades. I have shown some challenging examples like windscreen antennas, cable harness modeling, where through other means very efficient solutions are possible other than brute force application of computational electromagnetics. I have also kind of touched on multiphysics use cases, high performance computing in the last part on AI/ML, and kind of just as an outlook, I think computational electromagnetics and radio science in general have a brilliant future, of course driven through the ever more and more connected world, wireless sensors, wireless communication, so many applications that drive innovation, go into new design, explore higher frequencies, all this complemented with advances in novel computational electromagnetics techniques, also many of them being covered throughout this week in the different sessions, and this supported through advances in high-performance computing. There is also quantum computing, for instance, now emerging and coming up, and of course also AI/ML if used in the correct context. You know, I've also seen approaches, and maybe my last comment, you know, where someone says, oh, we don't need to solve Maxwell's equations anymore, we just put it into DeepSeek or ChatGPT and they will give us the answer. That is for sure not the case at the moment, at least, and it will still take some time. Thank you very much for your attention.
Thank you very much, Ulrich, for this excellent overview. We have time for some questions. Ulrich.
Thank you. Very nice presentation.
Can everybody hear him?
I'll shout louder. So, you showed one example with a dipole in front of a square plate. And you showed a UTD formulation there, or UTD result. What did you do with the corners in that case?
Yeah, let me see if I quickly find this slide again. The question related, if maybe not everybody could hear the back, related to this example of the UTD plate. This dipole antenna in front of a plate, and your question is to the spot. Indeed, the edges and corners did consider edge diffraction, corner diffraction, but the requirement, and I touched on that a bit maybe in the previous slide, you know, there are special formulations possible when these radiating sources are close to the UTD surface or even touching through image principle and so forth, which is accepted. However, they do not work if the source is close to an edge or a corner. So in this example, luckily, or maybe you could say I've kind of faked it a bit because I've positioned it. This dipole, if you move it closer and closer, it moves towards the center of the plate.
No, my question was specifically, do you have a corner diffraction coefficient that you apply in this case?
Yes.
And where does that come from?
Yes, no, there is corner diffraction, there is edge diffraction, but they are the standard formulations which still rely on an incident kind of far-field conditions. So if you were to move that source closer and closer to the corner, we will not get that good match down to fractions per wavelength.
No, but even with the distance, what is the standard formulation of a corner diffraction coefficient?
implemented that as part of my PhD in 1994. I can't give you the literature reference anymore. I mean, there are, I can't remember now which formulation. I know there are a few formulations, and with faceted UDD a few years ago, some of our team members revisited them again and compared a bit. I mean, they are kind of there to remove the discontinuity of the edge diffraction. You know, if the diffraction point, but I don't have offhand which one. But they are still based on far field.
I grabbed the microphone because it's a similar question to Olaf. Not to put you on the spot, but a very informative overview, as Ludger said. Appreciative of that. But I know that some very popular programs like TCRA and XPatch, for their high frequency, they don't use UTD or GTD. They use incremental length diffraction coefficients for reasons I won't go into right now. But I noticed you didn't mention that. Was that because it wasn't part of your PhD? Or?
No. I mentioned it kind of here. For the shooting and bouncing rays or ray launching geometric optics, one often uses either PTD or ILDC to take diffraction effects into account. So it is possible, of course, and we also have it in FECO, not as part of the UTD solution, but as part of physical optics and as part of the shooting and bouncing rays.
So you do incorporate ILDCs at times?
Yes.
Okay. Thank you.
No, it's important. And there are different algorithms, different methods, and I think it's again often, you know, when, especially maybe for the younger students, the fact that there are so many different methods is confusing on the one hand, you know, and I experience often, you know, people trying to put an antenna on a structure and they just use one of the full wave methods. Method of moments, and they wonder, oh, my computer has now been running for 3 weeks and it's still going on. And of course, switching to, as you said, you know, high frequency asymptotics and so forth will make a huge impact. But I think one of the, and actually this is, I should have put it into AI/ML. This is where I personally also see a big, maybe positive impact of AI/ML is to pack all that experience and knowledge when which method or when which diffraction coefficient maybe works best for which problem. Is it metallic? Is it dielectric? What is the angle? What is the frequency? You know, all this knowledge kind of automate a bit the decision which method to use when, because it's not, you can't just say, oh, these and these methods are outdated, they have no reasons to exist anymore. There are always many cases where exactly this is the best choice, but it's difficult if one doesn't have the experience to know when which one is really the best. Or it doesn't have to be the best, but at least you shouldn't pick the worst.
Thank you for a very interesting talk, very informative. About the AI/ML thing, I'm just hearing from hearsay that it has shown significant speed up, but then it takes a long time to train those computers. Is that still a fact? It may take you days to train a computer, even though when you apply the algorithm to your application, it's very fast.
Yeah, I mean, you are correct. Once there is a stable machine learning model, applying it is very fast. Training, I think the biggest challenge is still to create the training data. So not the mechanism of training the machine learning model, but the getting access and having enough training data available. And often it is created through computational electromagnetics, and then of course it might take, depending on the problem and the solver, minutes or hours to train a new sample class. Building the models is not, to my experience, that big a challenge. But I mean, there are also so many use cases.
Other further questions? One is there. Please try to speak loud.
So, my recommendations for what kind of Krylov solvers could be used for full wave problems?
Yeah, your question is which type of iterative Krylov solver can be used for full wave methods. It's also not so easy. There is also not that single iterative method that works best for all types of problems. I mean, we have, or in my experience, we have been applying iterative solutions to MLFMM type problems, to pure standalone finite element methods, but also to coupled finite element boundary integral equation methods. And it depends really. I mean, there are, of course, if you solve closed structures with the C-phi, it's easy to converge. I mean, in my experience, but that might also be, you know, if it's GMRS, FGMRS, restarted GMRS works well for MLFMM, but again, not. I've come across examples, if it's really complex, too many different materials, too many maybe small elements, larger structures, then biconjugate gradient stabilized is again faster, converges more reliably. I think that it's similar to the numerical methods. You know, there's not one solution fits all. It's really dependent on the problem a bit.
Okay, and I guess kind of related, I've been trying to one of the FGMs and whatnot solvers, comparing them to the direct solver, LU. Would I expect to be faster than the direct solver? Or is the main gain going to be lower memory cost?
The question is, will an iterative solver be faster than a direct solver? I think, you know, if you can apply a direct solver, you can, again, it's either direct full or direct sparse. Up to a certain point, they could be faster. There are certain methods where it's not even possible to use a direct solver. If it's just, you can't even store the matrix in memory. I mean, like multi-level fast multiple method, it's kind of, if you have a far-field interaction evaluated differently, you can't use a direct solver. Again, I think it depends a lot. I mean, of course, it also, one important criteria also is sometimes you want to solve the same matrix multiple times. So if you have monostatic scattering, you have an object that can eliminate from multiple angles, that is then that if you do the LU decomposition, you only do it once, and then you have a very fast back substitution for all the different angles. So there are other considerations as well, not just the convergence, that might lend to the decision which solver to use.
I have a final question regarding the domain decomposition. When you measure something and then look at the incident field, it should be, apart from measurement errors, an exact solution, right?
I mean, the coupling is neglected, of course.
But the coupling is included in the measurement.
Yes, yeah, but if you, the question was, you know, if you measure part of it and include it in the numerical solution, it should be the exact solution. I think the challenge is one measures, for instance, an antenna in a lab environment, which might be above the perfectly conducting one.
No, I mean,
and later you put this antenna on.
If you measure it in the original, then you have an exact
solution. Yes. If you measure a certain structure
then
in the final configuration, yes, then it's kind of, I mean, then I wouldn't call it kind of a model decomposition, then I would call it a validation campaign. You know, you validate either where you come from, you validate either if your measurements are not correct, or you validate if your computational electromagnetics solution is correct. Yeah. But of course you are correct. It should match them very nicely. But in the example I've shown, the antenna was measured without the reflector, and then the reflector was able.
Then you have the typical problem of these kind of solutions that you have not included in the copy. Okay. This I would like to close this session, not without thanking our speaker again. So we have now a break until 11:30, and then we have here the session Industry Meets Young Scientists in the room.